Good afternoon, everyone. I'm going to go ahead and make a few announcements and introductions while we wait for a few stragglers to join us. My name is Mike Zilmer. I'm a business development manager with Adaptive Corporation. I want to just take 2 minutes to tell you a little bit about our company, give you a broad look at what we do. Adaptive Corporation is a technology and consulting firm with a pretty broad reach. Help companies innovate, validate, and refine basically whatever it is that they design or manufacture. 5 bullet points on the left side of the screen there really do a pretty good job of covering the different types of solutions we work with. Virtual product development is typically referring to CAD and simulation or CAE software. We'll talk more about the simulation side in a moment. Enterprise collaboration and data management are fairly self-explanatory. They fall into the PLM side of the business. Then we have digital manufacturing, things for quality assurance and for quality control. And the metrology division works with high-end scanning technology. Some of them are even portable, so you can use it right there on the production line or out in the field. So we really have a kind of end-to-end solutions, but we work with companies to be as much or as little as what they need us to be. Our speaker today, Wayne Tanner, worked for Caterpillar. He started his own consulting firm in 2001. It's called Leading Edge Engineering. The simulation division of Adaptive Corporation is that company. So the two companies, the owners of the two companies met, and the puzzle pieces fit together quite nicely. And so they combine forces. So Wayne focused specifically on simulation software and services. Over the years, the software OEM started noticing that he and his team were quite good with the software. They started asking him to handle training and consulting projects for him, and eventually asked him to sell and support the software. The group of companies you see here is quite unique. I don't believe you'll find another company in the world that can sell and support both Dassault Systems, Simulia software, and the MSC software product lines. Woolstar Technologies here is, they have the TrueLoad software that we're going to be talking about today. And we do consulting work, consulting services. We can handle, run-of-the-mill stuff. We can also handle the highly complex and the never-been-done-before type of projects. We sell and support the software. Because the engineers are out there doing real projects with it, they're able to really help people implement the software and help them through all the difficulties from, technical support standpoint, or doing, customized training where we're training people on their specific models. And then offering, mentoring and things like that as well. So I'd like to go ahead and hand the ball over to Wayne now. Wayne is considered an expert in fatigue analysis and weld fatigue analysis. He, along with being the VP of simulation at Adaptive, he speaks at various technical conferences and simulation events throughout the year. What I'm going to do is I'm going to ask Wayne to start us off by sharing a little about his work at Caterpillar, some of the engineering and the testing challenges he ran into. They're very relevant to what we're going to be talking about today. So Wayne, I want to thank you for taking the time to be with us. Before we get started, would you mind taking a few minutes to share a little bit about what you did when you worked there, and from a testing and a simulation standpoint?
Sure, I'd be happy to. Thanks, Mike. Hello, everyone. Thanks for joining the webinar. We appreciate you taking the time to be on the call with us today. As Mike mentioned, prior to starting up Leading Edge and then coming to Adaptive, I used to work at Caterpillar as a mechanical engineer, performing design and simulation in the motor grader group. At CAT, we lived and died by weld fatigue and bolted joint issues, and spent a lot of time developing loads for our structure. Before I get too far on that, let me take a minute here and let's just talk about what a typical workflow simulation may look like. Most of you are familiar with having some type of CAD model, then moving into doing FE analysis using Abacus, Nastran, ANSYS, or any of the other dozens of solvers that are out there. Typically, you will have some loads that you'll apply to that analysis. Maybe they're some calculated worst case loads, maybe they're limit loads, maybe there's some inertial loading, etc. But somehow you've either measured or generated or calculated some kind of loads that you apply to the system. From there, typically most people will then go into potentially a fatigue analysis process where you're looking at then taking either combinations of these load cases and applying them and doing a fatigue calculation with them, or using some kind of unit load scenario where you then have time histories of loads that scale and combine on those unit loads. Output out of a fatigue process will be some type of life results in terms of hours, repeats, miles, etc. Then potentially you could go into some kind of optimization process. In this case, we're showing Tosca, and then go back into some redesign, analyze loop there. So while we were at Caterpillar, we spent a lot of time and effort trying to get accurate time histories of loads. We would take our machines and take pins, machine pins, so that we could, and calibrate those pins so that we could measure from the strain what load was coming through them. We would take any type of joint system, whether it's an axle or shaft or something, in machine areas where we could lay strain gauges on there. We had lay strain gauges on our hydraulic cylinders so we could accurately measure loads coming in through there. So we could get a full time history of loads for that structure for a complete event, and then be able to take that load data and cycle it back through in some kind of FE analysis or fatigue analysis, either at certain set points or a complete duty cycle. While we were there, for each one of these, for every vehicle and every load case or every duty cycle that we tried to validate, we would spend upwards of $250K on just acquiring the load data. And that doesn't account for any of the time afterwards. We would have to process that load data and validate it, and then input it into our FE analysis and into our fatigue analysis. So we were spending huge amounts of money and huge amounts of time capturing that load data because we thought it was so important. We had an internally developed tool that we'd use, but it was a little cumbersome and very hard to use. When I started this company, what we saw is that was a very difficult process for a lot of our customers to go and calculate those loads, and they didn't have a very good process on how to do it. What was even more worrisome was that these companies would typically use plus or minus one, or maybe a series of limit loads, and try and perform fatigue analysis on it, and then would really struggle with, why doesn't the fatigue results match up with what they're seeing out in the field? And so we really spent a lot of time then working with our customers, trying to say, really, what is your duty cycle and what are your loads? Once we met Tim and understood TrueLoad, we quickly realized that was a tool that replicated some of the tools that I had available to me at Caterpillar, and even went a couple steps further in automating the process and providing some of the tools to validate and confirm that we could get accurate data out of that. We use TrueLoad in our consulting business as often as we can whenever we're trying to develop load cases for our customers, and that's why we have a real appreciation for the tool. But before I get too far, I want to show an example that a customer sent to me last week. And this customer said, hey, we have a tube that we want to measure some loads on. They'd had some idea about TrueLoad, but they said, hey, we want to measure some loads. We really don't have a lot of time here, but we've looked up in our handbook, and round tube, we can put strain gauges on and calculate the torque load that's coming out of there. Is this process still valid for a square tube? I said, yeah, we can probably still do that for a square tube. We can put some stuff on. I said, send us the geometry. Let us take a look at it. So they sent us the tube. Like, okay, but the tube has some structure coming out of it, and they not only have a moment out here on the end, but they also have an offset load here. Okay, that we could probably still work with that. But then they came back and said, well, it's not really just that. We've also got some other components attached here, and we've also got some side loads coming in through this structure as well as some vertical loads. Okay, so now we're not just talking about a bending or a moment anymore. We also have a bending load. And then, you know, as you look a little bit further, well, they have some additional structure attached to the system, and when you look at the full system, this is what it looks like. Well, just like in real life, you know, this is a real life example. These textbook examples don't usually correlate very well to what you really have. So we went through and said, we really need to use true load for this, and convinced our customer that's probably the best way to go to place our gauges and go through that process. So as we look at different complex loading scenarios, I want to kind of show something that one of our other customers has used. So this customer, Trek, they have bike frames. They have very complex loads coming in. They went out, and before they found true load, went out and gauged up this frame trying to calculate loads coming into it. During that process, they had 20 or 30 different gauges that they're trying to locate and manage, a lot of different load cases. They're looking at the different quality of the data that they got. They have unique loading points for each, unique loading data for each load case, and it was impossible for them to perform this manually. And you can see in this type of event the kind of severe loading that goes into one of their structures. Now the good news here is this rider's okay. He gets up and no problems. But we wanted to show you this to show you kind of an example of some of the extreme load cases that happen. So let's get back and talk about a true load a little bit. So true load was developed by Dr. Tim Hunter through his 22 years at Harley-Davidson. There he is the chief engineer for vehicle structures, and when he left Harley in 2010, he founded Willstar Technologies. So Tim used true load. Tim, during his time at Harley, they would spend a lot of time building prototypes, and for them, what they called a prototype was essentially about 85 different motorcycles that covered the different variations of their configuration for each platform. And when Tim started the process, they were building about 6 different prototype phases. So 6 times 85, that's a lot of motorcycles. That's millions of dollars that they're spending. And they'd get through the process, and during some of those phases, they'd find, hey, their loads are wrong, or they're having cracking problems, or they're having failures. And Tim mentioned one instance where they're ready to roll the product off the line, and they found in the test phase, very late in the test phase, that they hadn't accounted for a different unique loading scenario, and they had to stop their production that they're getting ready into, and they spent several $1 million. Through that process, Tim started implementing the true load technique, and basically this is a technique that has been around for about 30 years. So Tim didn't develop the technique, but through literature found it and then was able to expand on it and make it a little bit more robust for their scenario. By the time Tim left Harley, they had, for a product launch, they had actually dropped their prototype development from 6 down to 1 prototype, and really that prototype was just for validation. Once they had better loading data, they could really utilize simulation to validate their structure, and then the prototype check, instead of it being a test, it really became a validation. So once Tim left Harley, he had built true load or implemented a version of true load in the old IDEA software for Harley. During that time period, they had moved over to Abacus. Once Tim left Harley and started Wolfstar and developed TrueLoad, he went back and Harley wanted to buy that version of it. So being a company that's somewhat risk averse, they said let's give it a try. We want to build a test fixture for it, and we want to validate that your process still works. And so what they did is they built this hangman fixture where essentially they bolted it onto the rear of a motorcycle, onto the luggage rack, and ran it around their test track to put some loads in it. The way they validated the loads that were coming into it is they attached a large mass to the structure and measured accelerations on that mass, and essentially used F equals ma to calculate the amount of force that's going into the system. Then used the true load gauges to say, is that the accurate force that's going into the system? They came back, had very good correlation with that, and as such are one of Tim's biggest customers. So this is a very early and big win for Tim to go through and to be able to sell his software back to his previous company and for them to go out and test it. And they did this without Tim's involvement, go out and test it and validate that this process worked. So let's talk a little bit about what TrueLoad is. TrueLoad is a linear system. TrueLoad works on the principle of a linear system of loads, works on the principle that loads are proportional to displacements, are proportional to strains, and strains are proportional to loads. So what it requires is that globally your structure behaves linearly. Now it can have local nonlinearities, local material nonlinearities, contacts, etc. But globally your structure behaves linear. So in other words, what we're doing is we're setting up an equation, F equals Kx, or if we rewrite that equation, strain times the correlation matrix equals F. And we're getting our forces from the strains in the system. Okay? So the strains come from test, correlation matrix comes from FE. We're able to combine those two to back calculate what our forces in the system are. So as we go through, let's talk about the TrueLoad process. I'm going to walk through a couple of steps of what that TrueLoad process looks like. Then we'll get into some examples and dig into a little bit more details of how TrueLoad actually works. The process step one is collecting the data, what we like to call a pre-test. So you're going to build some type of FE model and apply your best known loads and boundary conditions to it. So what direction you think, what unit loads you think are going to be applied to the model, what directions, and how that model is constrained. And this is one of the areas that TrueLoad really brings to the front is you really need to understand what are loads and boundary conditions of the model and how is it actually behaving. What assumptions can I make? And anytime we have problems with correlation, we usually can go back and look at, did we make the right assumptions here, and tweak those assumptions to get better correlation. But this is 90% of our problem, is understanding what are our actual loads and boundary conditions. So once we have our unit load model, we'll run what we call pre-test. That's essentially setting up, identifying, locating the gauges on the system, and identifying areas to locate it. TrueLoad has an algorithm to go in and place gauges in the best locations. And then it also has tools to tweak those gauges so that if you've given it areas that may be hard to reach, we can simply move those gauges or tweak the orientation of those gauges to be more conducive to applying in test. Once we've identified the gauge locations in TrueLoad, TrueLoad has some, in the pretest component, TrueLoad has some very nice gauge dimensioning tools that we can use to create a gauge map to give to the test department to lay them, or if you're a small company, you may go out and lay some of them yourself. Then we'll come back and conduct the test and collect this data. So now once we've collected our strain data, we need to go back in and calculate the loads. We take that collected strain data from the test and we're going to feed it back through TrueLoad. TrueLoad is going to then essentially multiply that strain data, so your strains, by our correlation matrix that we calculated in pretest to calculate these calculated loads and load time histories. general rule of thumb is we need about 1.5 to 2 number of strain gauges to the loads we're trying to calculate. Because we're trying to solve a linear system of equations, we need more knowns than we have unknowns. Once we've calculated that load data, TrueLoad has a very nice set of tools to go through and do correlation and plot history plots to validate how well is my system correlating. So TrueLoad automatically create what we call a cross plot. So that's our FEA strain versus our field strain. So the process for doing this is we plug our test strain, our field strain, back into TrueLoad, calculates the load time histories, and then TrueLoad will automatically feed those load time histories back through the model to get the FEA strain, and then calculate that strain times our field strain. And if we have a very well correlated model, that data should line up on a 45-degree line. Some cases it doesn't, where we may not be using the right assumptions. It also has some very nice tools to plot that field strain versus simulated strain, so you can see how well it correlates, or you can see areas where things may not correlate very well. And then, in addition, what's very nice about it, it has ways to automate that time history. So instead of resolving the model for a full time history, what it's doing is automatically scaling and combining your unit loads times the calculated load data to get full field strain, stress, displacement data for these for these duty cycles. So that was a brief look at it. I'm going to go in through some more of TrueLoad later and get into really the nuts and bolts and the details, but I want to kind of give you that high overview. So back to our simulation workflow, we've got our FE model. We're looking at fatigue results. TrueLoad now replaces our loads that were maybe calculated by hand with a plus-minus scenario or that. So now instead of having some worst case or static loads, we're now able to use TrueLoad to calculate a full-time history of loads to really get in and perform some detailed fatigue analysis with accurate load data. So the workflow then replaces any of the load data that we were calculating manually or with some hand calcs to an actual full data from a physical test. So what I want to look at now are some examples and applications of TrueLoad, how we use it, where we've had some customers with success, and several techniques that we've applied. One of the first projects that we worked on with Tim was calculating blade loads for a bulldozer. In this scenario, one of our customers was having a very difficult time calculating ground engaging loads and really correlating the model and validating that, hey, if we even went into a lab and applied a known load, we can get the same type of strains and load data back out of the system. So we went in with this customer and worked with them and said, okay, let's apply a series of gauges along the push beams and on the back of the blade so that we can go in and apply a known load and see if we can get actual strain data back out that would match. What we were able to do then is not only did we have our TrueLoad gauges, but we also applied gauges near some welds, essentially in some hot spots that we could use to go back and correlate our test data, correlate our model. And after we got done and went through a couple iterations where we had to tweak some of the assumptions that we put into the model and how some of the connections in the system were made, we found that we could very well correlate strains in the model with strains measured in the test. And we're within about 5% correlation when we looked at high strains in an area of high strain gradient near a weld. Another example that we have is a crankshaft example. This customer had known that they had failure locations For a long time, they were trying to figure out how exactly to solve that, what was causing those loads. But they couldn't get their simulations to match the test data and identify what was causing it. TrueLoad was able to go in and apply essentially the right recipe, the right combination of loads, and it happened to be a series of dynamic loads and static loads that produce the right combination to show what was going on. In this case, we used a set of modal loads combined with quasi-static scalar loads on top of it to come up and produce the right system. Not only did TrueLoad identify the proper failure area, it also identified a secondary failure area. And when we showed that to the customer and questioned them about it, they said, yeah, every once in a while we actually have failures there too. So we matched both failure locations and accurately predicted the primary failure location in terms of stress and life. Another example that we want to talk about is a customer of ours, Trek. They use TrueLoad to develop a better set of load cases for them to analyze their bike frame. Historically, what they've been doing, and in the bike industry this is very common, is they have a set of known load cases that all bikes are rated against. Essentially, these are static lab load cases, and you can go in there and measure strains on the bike, but bikes are rated by this essentially by how stiff they are. Where these loads came from, no one really knows. How well do they actually correlate to how well a bike is performing is very questionable. There was no side loads, no fork loads. They had a certain load that was applied. Our customer said really was questioning where did this come from and how close to reality are they. So this was what drove this customer into looking at how can we use TrueLoad to get a better handle on this. So when they went through the TrueLoad process, they set up a data acquisition system on their bicycle with 24 channels, 12 strain gauges, 3 triax accelerometers, a potentiometer, and a Hall effect sensor. They custom designed the wire harness and carriage system and really built a pretty unique data acquisition system to go on and be able to collect data as they went through some of these kind of extreme events. Tim has some more detail of this on his website. You can go check it out. But the kind of short and sweet of it is, after they went back, collected these results from the customer, from the field test, and compared those to the lab test. So in this case, here's the lab test results. Here's 2 events that they looked at with some jumps and side loads. They found that their field loads, in some cases, were 2.5 times greater than their lab loads. And the direction, orientation of the field loads versus the lab loads were significantly different. And it really caused them to pause and say, really, what good are all these lab tests doing us? Are they really validating their structure? And what they're able to do out of here is develop a new set of load cases to really analyze and drive their design process. Another example is customer errands. They had in this case, they had a engine deck that they're having trouble with. They were trying to understand what was causing some of the failures and what were the load cases that were coming into it. What they ended up doing is developing something very simple. The user attached a mass to this structure and applied a XYZ load to the mass, essentially representing acceleration of the engine as this structure went through loading scenarios. They then went out, used TrueLoad to identify, based on those 3 unit loads, identify strain gauge locations and placement and calculate the correlation matrix. They then went out, collected that test data, fed it back through the system, and looked at how well does that correlate. And what TrueLoad in this case is doing is calculating equivalent loads that produce that same strain history for that part. And it did it very well. very straightforward. In a short amount of time, they were able to develop an accurate set of fatigue load cases that matched up with the failure areas that they're seeing. What this allowed them to do then is use those simple load cases to go through and quickly redesign their structure, and within a matter of less than a few days, they're able to build 4 different designs, iterate through all 4 of those, find the best one, optimize that design, tweak that a little bit more, and then choose the best design to go back out there, make a prototype, and go back out and test. So what Trilo gave them is a set of nice load cases to go through the design process with, quickly iterate through their design iterations with confidence, and go back out. And instead of having to do 4 separate tests, really only do 1. So significantly reduce their test costs. One final example that I want to talk about is a wheel force transducer method. This method is something we've been working on for a little while. We have a rim customer that we've been developing it with, and we have worked with them to develop a way that we can place. Right now we're at 32 uniaxial strain gauges on the rim structure that we can turn that rim into a wheel force transducer. We are working with those 32 gauges. We can calculate continuous rolling and tire carcass loads that we can then resolve to XYZ or axle loads to replace a wheel force transducer. Right now, we have taken this process, as we've validated it analytically. We're working with, as I said, our rim manufacturer to do this process for them internally. We're also looking for other commercial partners that we can go and validate this process physically with them as well. So if any of you guys here on the webinar are looking at using wheel force transducers, we know how expensive they are. If you ever break one, they're very difficult to replace, and they actually change your loads as you're going into the system. We think we can use the physical rim to replace the wheel force transducer and get you better load data for significant reduction in cost for wheel force loads. So if you're looking to do that, we're looking for people to partner with that we'd love to work with you on. So I'm going to go through one final case study. This is the K-Tech Earth Mover case study. This is a project we did last year. Talk through some of the details of this project and show you how we were able to work with them to identify better loads and understand their system. So through that process, I want to show you a little video of what their structure is. So they make what's called a pull-behind scraper. In this case, it's hooked up to an ADT dump truck, and they actually push it with a dozer. And so in this case, this scraper, they have various sizes all the way from a 20-yard all the way up to a 60-yard vehicle, and they'll go through, load it up, have it push loaded with a dozer, and then haul that, anywhere from a quarter of a mile to a half mile, a couple miles down the road to dump it. In this case, this customer needed to understand time history of loading to their system. They had a couple of unique static loads that they were trying to apply, but they needed a much better idea of time history of loads. They needed to develop what was a representative duty cycle of the system. How does that duty cycle affect the fatigue life and do fatigue life calculations, and where can they then look at optimizing the system to reduce weight and cost? Because every pound that they have in their system means another pound that you have to carry around empty and full. It means additional fuel costs, less payload, less efficiency of the system. So the part we did two projects for this customer, one for what they call the C-frame, and then one for the tail. So what we're going to focus on today is the tail and looking at this weld met right here. So in this project, we had a couple of goals. one, create a FE model of the tail system that actually represented the welds, had a significant weld detail in there to do fatigue calculations, determine a full-time history of the loads on the systems using measured data, develop a duty cycle for them from this time history of loads, calculate fatigue life, and then work on performing optimization based on these load time histories. So we created an FE model of the tail system, and we applied a set of unit loads to the structure. So in this case, we applied a 100-pound unit load at all the attachment points in all the different unique directions that we thought load would come into the system. So we had about 32 different loads we applied to the system. From there, from those 32 different loads, we were able to utilize about 50 different strain gauges on there to work with that. So as we go through the process, we have a FE model with unit loads. We take that model into true load, do our virtual gauge placement, go through, calculate strain measurements, bring that process back into true load for what we call post-test, so calculating the load data, which then gets fed into, in this case, we're using FE-Safe to do fatigue calculations. And then we go back to the previous workflow we saw, some kind of FE tool puts into FE-Safe for fatigue calculations, life contours are output, and go through some kind of redesign process. So in our true load pretest, we identified strain gauge locations on the system. So we identified, like I said, about 50 different strain gauges that we applied to the system, and then through that, using true load, gave our customer a gauge map for every one of these strain gauges so they could easily locate them off of, in this case, instead of using the FE geometry, which is mid-planed and surface representations, true load gives us the ability to bring in the CAD model and dimension these gauges right off of physical CAD locations. So it's much easier for the customer to go through and place these gauges. All right, once we've placed the gauges, we went back out and did our strain measurements and recording, and to help us validate the system, we always took, in this case, a little bit of time of dead time up front when the system was empty, and a little bit of dead time when the system was full, just so we had some static validation points. Then once we fed that strain data back through, we calculated loads coming back out of the system. So in this case, this is what we called event 2, which is a push load with our D8 dozer. One of the ways we calibrated this, not calibrated the system, one of the ways we correlated and verified the true load was giving us the right answer is we looked at this time point here at our static payload. We knew from weight what that payload was. We wanted to be able to show that true load could give us that exact same approximation back. So we know that we're at about 70,000 pounds on the rear of the vehicle, and when we looked at true load with our two left hand and right hand axles, we needed to be, in this case, since we only have half of each axle load, we needed to be at about half that load scenario. And so the true load, the vertical load on the axle is 33, true load calculated 35. So we're within about 5% of our actual load. So we felt this was a very good correlation of true load, or a very good time point to show us that true load is giving us the actual data back. And when we plot, again, strain, our simulated strain versus measured strain crossplot, we get a nice 45-degree line that shows that we are within what we want to see. So then we went back through and calculated a bunch of all of our different events. In this case, we had 18 different events, went through and performed each event, calculated a time history of loads that we could look through. And the unique thing about this, this customer had really designed their system with the thought process that the D8 push load was the most severe event that this structure saw. So when you come back up in the video that I showed you earlier, you hit this thing with the dozer on the back end, that was going to be one of the most severe load cases that they saw. And they really designed it with about 4 or 5 different back of the napkin hand-calculated static loads, and that one being the severest. What we found on this system as we went out and measured loads, that load case was by no means the severest. What we found is that their actual hauling when the system is empty were the most severe load cases, because this vehicle travels up to about 20 to 30 miles per hour empty, and when it hits bumps, this system really dynamically excites itself, and loads that we see through the system at that point are much more severe than any of the loads that came through the system when it was loading or loaded, actually. So it really changed how we looked at the load cases and how the loading on the system was applied, and how we'd go through and design and look through that. So what we're able to do is pull out a series of not only static load cases, but also develop develop a duty cycle for the customer and take all the events, combine them together to get to about 1 hour of operation that represented the full combination of the events that this vehicle saw within an hour time frame. What this gives us is a convenient way to measure life of the system that is relative to essentially the marketing life that they want to portray to their customers. So instead of talking in terms of cycles or repeats, we can talk in terms of hours, which matches up with their marketing side of the system and their warranty side of the system of saying, we're going to warranty and market this structure for 10,000 or 20,000 hour life. And so by using FE-Safe and creating a duty cycle, we're able to match that same terminology for the customer. So basically our fatigue calculations, we're going to take our data sets, our unit load. Our data set is the unit load of, in this case, Abacus results, but it could be Nastran, ANSYS. We're going to look at fatigue results, so repeat events in that duty cycle, what we call elastic block, or 1 block per each road event. Then our duty cycle gives us our entire duty cycle, essentially the 1.1 hours of operation. From that scenario, then we have to get to that scenario for each one of these events. We have all of our unit loads, and each one of these unit loads are being scaled by the time history of load calculated by TrueLoad. So then, as you can see, as you've seen earlier, TrueLoad can come back in here and create an animation of that event that we can easily process, look at displacements, say how well does that match up with what we saw, and it's much easier to grasp and understand how these loading scenarios are affecting your system and look at those displacements as it goes through that entire time history. From there then, with that full duty cycle of events, we can calculate fatigue lives, look at some low fatigue life areas, and work with our customer to improve those low fatigue lives. And then, as you can see in this system, a lot of the areas have very high fatigue lives. So blue is, in this case, our very high fatigue life areas, which gives us a lot of room for optimization. And the next stage of this process then, and one of the areas that we identified, is optimizing one of their welded structures in back, replacing the entire structure with a casting. Not only can we reduce the weight back there by about 50%, we can also significantly reduce their processing costs, excuse me, the welding and manufacturing costs. One final scenario as we go through this TrueLoad process, what I want to talk about is some additional functionality in TrueLoad that I didn't hit on here. Sliding load functionality. We also have sliding load functionality built into TrueLoad. We can take areas along the system where we may have sliding pads and unitize those loads and develop a set of scalars for these unit loads to provide sliding loads. And then in addition, we have hybrid loading functionality where we can replace any single unit load or load that's on the system with a physical measured load. So in this case, say you had a hydraulic cylinder and you were measuring pressure or load on that cylinder, we could replace that measured load with a true load calculated load, so we could reduce the gauge count that we needed for that system on those loads. One thing I'm going to break out of the PowerPoint here real quick, I also wanted to show that a very neat process out of TrueLoad is the HTML report. I feel that Tim doesn't talk about this enough, so I want to point this out a little bit. But we have out of TrueLoad, every time you run it, it automatically generates you a report. It's not maybe the prettiest report, but it gives us a very good set point to understand what was in that TrueLoad model, what was in that run, and talks about all the unit loads that are applied. We have our correlation matrix, calculates all the strain gauges that applied to the system, gives us a load sensitivity chart, and then calculates and shows us all the loads that came out of that system, out of TrueLoad that TrueLoad calculated, so essentially the load scalars. And then as you scroll down, gives us load correlation charts, so strain correlation charts, identifies channels, strain gauges where we had very low microstrain, so they may not be relevant, identifies ones that are very high microstrain that may be in some of the yield areas, and identifies our best and worst gauges, so in this case 3% error, in this case 13% error, calculating our cross plots automatically for every single channel, as you can go through and see. And then at the end of that, giving us just some static snapshots of gauge locations. So it's a very nice automatic documentation that TrueLoad applies that you're not going to see in some of the other tools that are out there. There's hundreds of thousands of potential applications. Just to name a few, as you saw in some of our examples, we have bicycles, there's wheels, rims, construction and mining equipment, trains, automotive, aerospace, industrial equipment. We think we can apply this system to heating and AC, compressors, etc., offshore wind applications. So anywhere where you need to develop load cases and loads for your system, we think we can use TrueLoad to help do that process quicker, faster, more efficiently, and significantly reduce your test costs. Some of the available platforms that you'll find TrueLoad on is Abacus CAE. We have a HyperMesh version as well. We have an ANSA version. So in each of these scenarios, these pre-post tools, TrueLoad runs as essentially a plugin or an application inside of these environments. We also have a standalone version that will be released in Q3. So the standalone version will allow you to take in any results database, say an Astran OP2, an ANSYS RST, an Abacus ODB, take in that unit load database and go through the TrueLoad process on that of identifying gauge locations, bringing that strain data back in, doing the post-test load calculation results, and then outputting correlation data. For customers who want to work with us, we have several different methods of deployment. One, you can hand us your FE models or your geometry, and we can do everything from running TrueLoad, helping you apply strain gauges, and then delivering you load data back, or even in the case of what we showed with K-Tech, going through and optimizing the structure. Two, we are a reseller for TrueLoad, so we can provide you with the software, where essentially we provide you with the software, give you some training, get you up and running, and you do all the results. We have several customers who are doing that process. And then three, somewhere in between, or maybe you may be building the FE model, we do some of the TrueLoad component, you bring it back, or we do some of the hybrid, maybe fatigue calculations or whatever the case may be. So somewhere in between with training or other options. Like I said, these versions can work with whether you're an Abacus, Nastran, and House. We have the tools to work with really any of the 3 or 4 main solvers or anything that HyperMesh and ANSA will support. With that, I'm going to turn the presentation back over to Mike and let him put in some closing comments and talk about some upcoming events that we have.
Well, thank you so much, Wayne. I really appreciate you spending the time with us today. Yeah, as Wayne mentioned, we have a couple of events coming up, Dayton, Ohio on May 3rd, and then Milwaukee May 1st, or excuse me, May 31st. What we've done is we put what Wayne, portion of what Wayne shared today into a complete simulation process where we spend about a full day. It's a no-cost event, and we have 3 different speakers. Wayne Tanner is one of them, the creator and owner of Woolstar Technologies, Tim Hunter, and then Darren Simone will be our multi-body dynamics analysis expert that would be doing that presentation as well. And again, these are no-cost events. It's really a look at laying out a complete simulation process from load development, finite element analysis, fatigue optimization, and then correlating. We are working on the landing page for that right now. What we will do is we will send everyone out who attended the webinar today. We'll send you an email that'll have the link to a recording of this webinar, as well as a link to a landing page for these events. Of course, we're always available to have one-on-one discussions with anybody that has additional interest in any of these areas that we've covered. My contact information is down there below. Feel free to reach out to me directly, and I'll put you in touch with the right people. At this point, we've still got about 10 minutes left till 2 o'clock, and I'd like to open up the floor to any questions that any of you may have. There's a spot on there for anyone to type in questions. I think you can raise hands as well. We'll give everybody a minute to push any questions in that they would like. Again, we appreciate everybody taking the time to be on the call with us today. We'll make the recording available to you within a couple of days. Looks like we have one question here. Wayne, it's kind of talking about the various different software tools that were presented throughout the presentation. FE-Safe and Abacus and ANSYS and NASTRAN, all that. The question is basically about, are there other programs out there that can do this? And what programs can we interact with? Looks like from an FEA standpoint as well as a fatigue analysis software standpoint.
So, like I said earlier, the programs that the FE solvers that we can interact with are anything that can be read by the platforms that we're on. So in this case, in the platform of HyperMesh and ANSA that we have today, any of the formats that they can read, which are all the main solvers: Abacus, NASTRAN, ANSYS, LS-DYNA, PAM Crash, and probably a few others out there that I'm not naming. In Tim's upcoming TrueLoad standalone version, I believe that's going to be built on something called CE-Tron, and that will by default be able to handle Abacus, NASTRAN, and ANSYS, and potentially a few other readers as they are added to the system. As far as fatigue tools, what we're doing is with TrueLoad is we're producing a set of load data. That load data can be in a text format. It can be used by any tool that can read a text format. In TrueLoad, we're automatically formatting it for FE-Safe. We could very easily automatically format that for ENCODE or any other FemFat, any other fatigue tool that wants to read it in. Or, as I said, it could be in text format, so we could slice it so you could grab unique static load cases to apply back to an FE model. And we're also working with Tim to try and allow us to take a static snapshot and actually produce, in NASTRAN speak, the case-controlled portion of a FE model to apply back to that as well. So we're almost completely open in terms of tools that we can work with. I think one of the parts of the question that you asked, Mike, is what other types of competing software out there for TrueLoad are there? There are a couple other competitors. One of the things to note is the strain correlation, our matrix coefficient calculation this methodology has been around for 30 years. FE-Safe calculated correlation matrices and still does by default for free in the software. ENCODE has done that for years as well. No one really used either one of those two processes because they didn't have all the gauge placement, gauge mapping, post-processing automation tools that exist on there. Since Tim came out with his software, ENCODE has dusted off their version and applied some other routines on it. I still don't think they have all the post-processing capabilities, gauge mapping capabilities that are available in TrueLoad. I've seen some of it. We have several customers that have tried to use it and just really haven't been successful at it. I think ENCODE just released their gauge mapping, our gauge location algorithm. I'm not sure how well that works yet, but we'll see how that competes with TrueLoad in the future.
Okay. Well, and I would also add to that Wayne has to consider that he's not just selling software; he's out there running it and using it from a consulting standpoint. So, to maybe elaborate on the answer to that question a little bit is to say that he can choose whichever software program he wants to use for consulting projects, and he and his team have selected these particular tools that you saw on this presentation for various reasons. So, he could go out and use the ENCODE process, but again, kind of what he said there is that it's just not, from his understanding, is it's just not there yet. Looks like we haven't had any other questions or anything come in, Wayne. So I think you've covered everybody. Guys, if you have any other questions or anything, please feel free to send them in now. We've got about 4 or 5 more minutes left on the webinar. What we'll do is we'll leave the session open, and if any other questions come in, we'll answer those. But based on what I'm seeing right now, no other questions coming in. So Wayne, you must have done a great job on covering everything and making it make sense to everyone. So what we will do is, like I said, we'll leave it open for a couple more minutes, but for those who want to go ahead and sign off for the day, we'll let you get back to your day and get back to work. Thank you again for your time, and if there's anything we can do to help, don't hesitate to contact me.
Yeah, thanks a lot, everyone, for your time. We really appreciate you spending the time to listen to us.
All right, Wayne. Well, it looks like most everybody's dropping off now, so I think we can go ahead and conclude the meeting.
Okay. Thanks, Mike.
All right. Thanks, everyone. Take care.